To understand a Tier 4 water-cooled chiller plant, we have to stop looking at it as a collection of independent machines. It is a single, interdependent thermodynamic and electrical system that must act as one unit. Moving these massive amounts of heat out of a modern facility requires immense kinetic energy and highly synchronized infrastructure. This graphic maps the entire heat path boundary. We track thermal transfer from the IT load to the atmosphere by isolating specific loops: the server air loop, the chilled water loop, and the condenser water loop. Every point is governed by strict control boundaries. Local controllers dictate safeties, while the central system coordinates operations. Looking at the internal mechanics of a centrifugal chiller, a sealed refrigerant absorbs heat from the evaporator, is compressed, and transfers energy to the condenser. The chilled and condenser water never mix. To meet compartmentalization requirements, these loops use motorized isolation valves. If a frame leaks, it seals without draining the main loop. The total system efficiency formula divides the combined power of all chillers, pumps, and towers by refrigeration tons. Advanced frameworks require the ecosystem to hit under 0.68 kilowatts per ton. This target must hold during part load operation. Redundant systems rarely run at full load, so the integrated part load value must remain below 0.35. Procuring high-performance individual machines yields no benefit if the integrated thermodynamic boundary fails to meet these total system efficiency targets. The entire chain must perform as one. Maintaining the reliability of that heat transfer requires adhering to strict chemical constraints designed to maximize water usage effectiveness. We measure this efficiency through cycles of concentration, or COC. The absolute maximum cycles a plant can run is strictly dictated by the lowest chemical tolerance in the makeup water, whether that is calcium hardness, alkalinity, silica, or chloride. This graphic illustrates running a system at 5 cycles of concentration versus 10. Doubling to COC 10 results in a 55.6% reduction in blowdown water, cutting waste. But achieving these savings safely demands automated filtration and metallurgy compliance. Without precise chemical management, high cycles lead to catastrophic scaling and corrosion. Detailing physical qualifications, this chart shows environmental restrictions on refrigerants, guided by LEED baselines. Targets require utilizing refrigerants with a global warming potential below 700 and strictly limiting the charge ratio to less than 1.8 pounds per ton of cooling capacity, maximizing sustainability. Containing highly pressurized refrigerant requires serious physical infrastructure, including certified seismic bracing to ensure violent structural shifts during an earthquake do not fracture critical lines. Sustainability is a chemical and structural engineering problem. Efficiency targets hold value only if the fluids driving them remain mathematically balanced and safely contained within the pipework. The ultimate proof of a cooling system's resilience is the integrated utility loss test. This live simulation measures whether the entire plant can survive a total blackout and restore flow without breaching the IT thermal envelope. This flowchart maps the blackout test sequence. Before pulling the plug, the team must confirm strict Level 1 preconditions: a verified thermal margin, a normal operating lineup, and a synchronized time zero timestamp established across every data log. At time zero, normal power is severed. In the first 2 seconds, alarms cascade across the facility, but local safeties and controllers must rely on their onboard power to forcefully maintain their logic state and prevent a full memory wipe. Looking at the rapid restart timeline, we see that between the 10 and 15-second marks, the backup generators spin up to full speed, and the alternate bus power finally becomes usable for the mechanical systems. This diagram of electrical resilience illustrates how that power is delivered. It requires independent A and B power paths terminating directly into the chiller load, completely eliminating any shared single-point control gateways. Restoring power is not enough. The quality of that power is heavily scrutinized under the IEEE 519/2022 standard for total harmonic distortion, measured at the point of common coupling. Built-in active front-end variable frequency drives clean up the waveform, ensuring that harmonic distortion remains below 5%. Without this cleanup, dirty voltage distortion will prematurely trip the backup generator breakers. Mechanical recovery is entirely subordinate to power quality. Introducing highly distorted power during a massive plant restart will instantly abort the entire cooling recovery sequence. Advancing the timeline to the 15 to 25-second window, stable generator power is now flowing, but the chillers themselves remain strictly locked out by the central control system. Before a chiller receives a start permissive, the system executes path verification. Motorized valves stroke open, and independent sensors must physically prove that water is actively flowing through the chilled water, condenser water, and tower loops. Restarting the hydraulic flow across the facility is a massive kinetic event. Thousands of gallons of water must forcefully surge through the industrial pipes. This graphic breaks down the thermal write-through. While the chillers are offline and the pumps are spinning up, a thermal energy storage tank, or TES, actively absorbs the IT heat load to bridge the gap. Sizing this tank requires exact mathematics, multiplying the total cooling load by the time required for restart, and dividing that by the product of water density, specific heat, and the usable delta T. The dynamic proof rule for this discharge phase is absolute. The rack inlet and chilled water supply temperatures must not breach the approved thermal envelope at any point while the tank is discharging. By the 30 to 45-second mark, flow is verified and the lead chiller restarts. To meet this tight window, data center chillers are programmed to bypass the standard hot start delay timers used in commercial applications. The final milestones approach quickly. The mechanical train must reach 80% capacity stability at 75 seconds and achieve 100% of the required plant capacity by the 180-second mark. Surviving that 3-minute window is an exact orchestration of fluid physics, precision electrical switching, and carefully calculated thermal buffering. When all systems function perfectly, the plant recovers in under 3 minutes. But data center engineering requires planning for the moments when the timeline breaks and automated recovery sequences fail. Consider a scenario where a primary chiller faults upon receiving power and completely fails to restart. The unbending operational rule here is to never force an override on original equipment manufacturer safeties. The correct protocol is to isolate that specific chiller domain, immediately start the standby train, and rely on the thermal energy storage buffer to buy the necessary time. Another critical failure mode occurs when heat rejection is suddenly constrained, such as losing a cooling tower cell while the facility is under full IT load. The escalation response requires maximizing flow through the remaining condenser water paths and verifying tower basin levels. IT load shedding is executed only if thermal maximums in the data hall are definitively breached. A third major threat comes from rapid water quality events, where sudden particulate influx causes catastrophic fouling, severely altering the plant's heat exchange efficiency. Unchecked water chemistry will aggressively destroy high-performance mechanical equipment from the inside out. The emergency protocol requires halting makeup water loss immediately. This protects the pumps from net positive section head cavitation and stops permanent scaling from baking into the chiller tubes. During complex cascading failures, emergency operating procedures share one primary directive: prioritize IT thermal stabilization and life safety over attempting to fix the broken machine on the fly. The biggest vulnerability in facility management is the assumption that simply purchasing N+1 backup equipment guarantees data center survival. Redundancy is an active, verified state, not a static count. If the control logic cannot accurately detect a fault, automatically isolate the broken pipework, and reroute flow, the backup equipment sitting in the room provides zero protection. This is why operators rely on a strict return to service gate. It is a rigid procedural checkpoint that dictates exactly when a repaired system is allowed back into the critical rotation. Work orders are closed, hardware safeties are restored, water chemistry is verified by labs, and mechanical isolation valves are only removed under explicit supervisory authority. Even after repair, a full functional and rapid restart test must be independently passed before standby readiness is officially signed off and trusted. Only when all these conditions are met does the facility actually achieve fault-tolerant harmony. Designing for continuity demands an unyielding commitment to mathematical calculation, automated isolation boundaries, and continuous field proof.